welcome to today's webinar. My name is Bastian Kuhn. I will show you today timber floor calculations in RFEM 6, and my colleague Gerhard Rehm can introduce himself.
Yeah, hello. Yeah, my name is Gerhard Rehm, and I will be responsible for all your questions today. And Bastian will explain you now how you can ask the questions.
Exact. Thank you, Gerhard. So, in case you want to ask questions, you have a register called questions. You can ask them there, and my colleague will try to answer them all. And in case we cannot manage to answer all questions because there are so many, we will send you an email afterwards. So every question gets answered. I would like to introduce you to the exhibition at Digital Bau in 2 weeks at wait, we can also put the camera on. Yeah, now it's completely out in Cologne. Cologne is always a good place to be, especially today, as today the carnival starts in Cologne, but also in 2 weeks. If you book a live demo, we can present you our software much more detailed, and you will get a free ticket as a gift as well. All right. The content we want to show you today is modeling of a 2D system, or not really modeling. I want to show you how to extract effects of a 3D building into 2D, regard all the load transfer points, and then design it. Design timber for ultimate limit states, serviceability limit state. This includes vibration analysis, then fire resistance design also for CLT. That's the big new feature we want to show you today, that this is possible for surfaces, and we want to bring that all into a printout report. All right. Okay. So then I will shut off the camera and jump into the program. Before we jump into the program, the project that I want to show you is also on our homepage under customer project. It was built last year. The static analysis has been done by the engineering software, by the engineering company Pirmin Jung. They're using our software. Yeah, that's the key. And this is the building, 13 stories. The point we want to take a look on today is that there is, or what makes also the building quite interesting, is that there's a smaller part that is upon the bigger part, and we want to take a look on this story 3 here. So how can you do this? Now you can first of all make it with model it 3D and regard all construction analysis, stages analysis, all this stuff in the 3D model, or you can model it 2D, and then you have to connect each story via the option load transfer. And this is the option that I'm choosing here today. Today, I'm only looking for vertical deformation forces. I'm not looking for horizontal forces for the stiffening of the system. I want to do this in a separate webinar later this year. Today, only vertical, deflection and vibration. So wind load and earthquake we will not consider here today. As I said, I want to calculate that in a 2D structure, but with 3D effects. Therefore, just to give you an imagination of the structure, I just copied the top stories 4 to 13 in a separate position, that I make a simplified load case there for the self weight 4 kilonewton per square meter, and the live load 2.25 kilonewton per square meter in each story. Gives you approximately a height of 25 meters of the story 4 to 13. And now how can you get the force from the story 13 to the story 12 and so on? Therefore, I created separate 2D positions. Here is the story 4, and I summarize them all. I want to show you that in the Windows navigator. So I have here story 4, story 5, story 6, 7, 8, 9, 10, up to 13, and connected the forces from the top story above the story 4 via the function here import support reactions. Because there I can say, okay, I'm connecting the story 5 here, so the resulting forces from the story 5 into this position, story 4. And then I can say, okay, in the model with story 5, I have support nodes, support lines, and then I'm importing them to the current model right here. And I can automatically transfer the load case from load case 1 to load case 1 in the new story, and so on. This is how it works. I will put on the forces or the load, and here you can see that I have point loads and line loads, and if I activate it, also I have also surface loads, and this is I told that already, the 4 kilonewton per square meter for the self weight and the 2.25 for the live load. But we just want to concentrate for the load that's coming from the other stories. You see here that in this part, I also defined nonlinear nodal support behavior. It would also be possible to regard the settling or the construction stage via a spring constant in here. All these points would be possible to be regarded and still transfer the load from one story to the other. Okay, now when we go into the position that we want to analyze today here, I think it gets much clearer, because I know it can be quite confusing, especially if you have not seen it before and did not work so often with did not work with RFEM 6 before. You see here, I'm in the load case 1 self-weight. Also here, I have, when I activated the force in the first load case 4 kilonewton per square meter and 2.25 in the second load case. These are the only two load cases I want to analyze today. I said it is a simplification today. Okay, I think the easiest way to regard that or to understand what I'm doing here is to take a look at the point load. So we have 1.68 here and 2811 there. Now when we look to the previous model from the story 4 and take a look at the reaction in the load case 1, you see that I have 1.68 here, and if we turn it a little bit around, 28.11 here. So that really is the load transferred from this model into the other. And maybe we take also a look to the line load here. So 591 here, and then I think it should be enough. And right here, whoops, you see also 591. So yeah, that fits. The load is correctly transferred from, I would like to say, story 13 to this part that we are analyzing here. Okay, to the structure itself. Now that we have such a whole bunch of questions already, it's hard for me to follow them all. All right, there they are. I would like to show you also the dimension of this structure that we are analyzing today. Therefore, I just shortly switch them on. It has a length of nearly 30 meter and a width of 12 meter. I have several CLT plates in here. They are divided in an order that they also can be produced and brought to the assembly. That's essential that this is possible. And they are connected in between those connecting points via screws, and the screws in our software are modeled via line hinges. There's another webinar where I get into this much more detailed and also use a little bit of a script function in order to calculate them. But today I just took the force from the existing project, or not the force, the spring constant over from the existing project. So in X and Y direction, I defined this spring in here. So that's why it's connected. The CLT plates themselves, I generated with our add-on multi-layer surface. Maybe I go a little bit into the basics data here. So it will be this add-on multi-layer surface, and I'm designing all this stuff in the add-on timber design. And when I defined this layer, I have a database here with all the producers that we are offering right now. So you see, it's even possible to have a producer from Switzerland, maybe not this one, Schillinger, for example. But of course, all the European producers. And if you want to design in America or North America, Canada, then you can also have producers from there. Right now here, I choose the plate from the company Derricks. And this gives me a certain amount of stiffness. I have other options here to regard the failure of net sections and failure include contact surface. This is once again more for the webinar of the stiffening system for horizontal load, and I don't want to regard that today. But what I want to show you is that these layers here will generate a stiffness that we export into RFEM. So you see that this stiffness, if we're just looking for the top bending elements in here, you see that D11 is way more stiffer than D22. So the stiffness in X direction is higher than in Y. That's timber, right? Obviously. There's nothing so fancy and new. But now when I'm as a designer working and constructing it, you probably realized already the blue arrows here. It was in previous versions always hard to know how I'm assigning the plates. It's if we look for the downstand beams that I have underneath those plates in here, you see that there's a downstand beam that is supporting this plate and this plate and this. Because of this connection point in here, it would not be possible to design it, or well, economically to design it without this part. That would be quite hard. At least with screws, it can be a problem. And therefore, this beam was arranged in here. It's a continuous beam from this point to this point. And now when you want to arrange the stiffness, you probably say, okay, I have the span in global X direction. That's where I want to arrange my stiffness. So it's completely right what we did in here. And we can also have it much more detailed if you want to say, okay, I want to look at each layer. I would just directly jump back to the thickness again, or maybe I can even have it here and then jump. That would be possible here. So you see my first layer is oriented in 0 degree. The third one is in 0 degree direction, and also the fifth one. And this is then the red arrow here. And the soft layers of the structure, which has less stiffness, is then this direction. So I don't want to get too detailed in it, but in a CLT plate, you have always the you are just regarding the stiffness in X direction. And because of the orientation of 0 and 90 degrees, you still have stiffness in Y direction. You saw that in the stiffness matrix. So what I actually wanted to show is that you will directly get very comfortable the stiffness direction, and then as a constructor, you can directly see, okay, here it's correct to orient it this way, but here probably not, because there I have supports completely here over the whole length, and I also have supports here, and there I definitely want to change that. How can you change this? If you assign specific axis and define it here by 90 degree, the whole composition is changed and you see it directly that the stiffness works. All right, that is the plates. I also defined supports, well, just simplified, also only vertical and not movable in X and Y direction, because I think this is, as we are only looking for vertical forces and deformation, this is okay. I will generate the mesh just to show you another part, what I made in this model. I certainly did take the whole load, once again, the example of the point load of 1.68, and defined it with a tiny little eccentricity to the support. In reality, when you are constructing this, you probably do not assign it to this node. What's the number? 439. You would probably assign it to the node 215. But I did it this way, and this will definitely give you a singularity, which will never occur in the real life. And either you can put the force directly to this node, or if the distance gets bigger, there's also the option to define a surface result adjustment. This is what I did in here. All right. And I use this surface result adjustment wherever I have these problems. But I want to show you with this the advantages of this 2D system in here. When I have it in a 3D, it could be quite a lot of more work to regard it. And also when you say, okay, a downstand beam here, maybe I don't want one, this would also be easier in this position in here. Okay, we switch off the load again and come to the beams forces we did. I said it already, the beam is supporting the plates because they have connection points in here. Otherwise, it would not be possible to assemble them, or to produce them and to assemble them. Both would not be possible. And of course, the engineer divided the beam in these connection points. It is not possible, necessary with RFEM 6 to divide it, but he did it. And now, how do you regard that as a continuous beam? You will use the option member set. Sorry. Okay, when we are already in member set, we can directly take a look at the design types of this beam. We don't want to look for stability today, as we do not have any kind of buckling. And we could also argument that for lateral torsional buckling, it does not play a role in here because we have constructive fixing on the top of it, so this will not occur. That brings us directly to the design configuration. Well, the ultimate limit state configuration is then also not so much to do. You can consider the system strength factor. That would be something probably quite relevant in case we getting right to the borders of the loading with the members. As I said, stability we do not do. And we have also the system strength factor for the surfaces. So it's always divided ultimate limit state, serviceability limit state into the definition of member and surfaces. It's more or less the same what you input in here. Fire resistance verification, configuration, that is the new point what I want to show you for surfaces. Therefore, I will not show that in the members right now. For the member, I want a required time of fire resistance of 60 minutes. And because it's covered on top by the plate, I skip that and say it's only burning left, right, and bottom. And 60 minutes, that's what I'm defining. Then what else can we define for the beams? We can define a member support at the member, start and end in this case. Here I said, okay, I have a support length of 30 centimeters, which is quite long. Possibly you want to reduce that later on. And I'm using shear force reduction that I can always activate. In case I have a shorter support length, I would maybe also want to reinforce the support via screws or with a user-defined strength. All this would be possible. And in order to regard the softwood, I can also increase the factor KC90 by the factor 1.5. All right, deformation is nothing I have to do much special on today. I'm just using the reference lengths. I will come to that when we look for the surfaces. And we will take this one here, this surface, and take a look for the design configurations again. The informations of the thickness I showed you already, just so that you know what we are defining here. We have this reduction factors in here, which play a significant role for the design. That is all transferred into the stiffness of the structure. Okay, ultimate limit state, serviceability limit state, I showed already. There's not much special to say to, but fire resistance. This is the main reason that we are doing this webinar here today for you, because we are really happy that we are able to regard fire resistance verification for CLT plates now, and we can regard it now correctly with correct reduced stiffness and all these points. I will come to that once we did the verification or have the verification ready. So I'm saying I want a required time of fire resistance with 90 minutes, which is quite long. And the default setting here is non-heat glue, not the glue, but the glue or adhesion of cross-laminated timber, which means this is the standard glue taken by the producers. So be aware to take this one. And the burning rate that we have in here, we can also control that in the standard parameters, and it's probably quite interesting to take a look into that. The burning or the charring rate is for cross-laminated timber similar as for softwood, 0.65 millimeter per minute. So you say 0.65 millimeter per the first 25 millimeter thickness. Then when one part of the structure is burned, or of the layer is burned, it comes into the area where the glue, the adhesion works, in the connection of the two boards, you have to you have to double the rate, or maybe there are other rules where you even have to increase it. So you say not 0.65, but you say in this area where the glue is, you say 1.3 millimeter per minute. So that's quite a lot. And that's how it is regarded. In case one layer of the plate is burned nearly completely, maybe we take a look to to the layers again. So if you say, okay, the bottom layer here, where I am with 4 centimeters thickness is burned completely, then of course it cannot bear any force or any stress anymore. And then there's also the rule to say, okay, when it's burned equal or less than 3 millimeters, it has to be completely skipped out of the design for the stiffness and the stress. So that's quite important. Okay, and we want non-heat adhesion. The fire exposure, well, that's now quite similar to what we had for the members. On the top, I probably have some kind of planking or whatever. On the bottom, that is where I want to do or have the fire resistance verification. In case the bottom is also planked by, for example, gypsum or something else, you can calculate an insulation coefficient according the, once again, for example, the planking thickness, and then it's the factor K2 should be less than 1. Okay, but here today we say, okay, I'm working with this and we will try this one. Okay, this is the very important fire resistance, and we will do the combination, do the design, and then come definitely back to this configuration and take a look on it again. Deflection was predefined with the maximum boundary length, which is all right in here. It's from this to this point, 4.8 meters. Of course, and in the most of the cases you would want to have it, you can, also select a length, but you see here, this line is 4.8 meters, so you can really take it this way. Okay, and the service class is similar as for the downstand beams, 1 in this case. All right, this is the point, and we will get to the combination. I hope I did not miss important stuff, but I don't think so. Okay, we're doing a combination according to Eurocode 5 with the German annex. Of course, a whole bunch of other annexes are possible, and a whole bunch of standards for any other country is possible here. Okay, once again, we have only load case 1 and 2 for sake of simplification. Design situation is predefined with permanent for ultimate limit state, and in Germany we have 3 combinations for serviceability limit state characteristic, which is the initial deformation of the structure, and quasi-permanent and characteristic quasi-permanent with regardance of the creeping. So these 2 serviceability limit state verifications will also regard creeping. The creeping you can define in the basics with settings for timber structure. In case your structure gets nonlinear, you have to regard the creeping factors in stiffness modification, but we do not have this case here. And of course, we also want to do fire resistance verification. Therefore, once again, in Germany, it is recommended to use the accidental combination for fire with psi11, which means that your factor psi11 is put in front of the summation. But of course, it's also possible to use the other summation where you have it in the summation of it. Okay, so this is the one we are using here, and then we can do our combination. Yeah, quite nice, quite short, not much to combine when you have only 2 load cases. And then the only thing left to do is go into the timber design and say what you want to verify in here. So we want, once again, verify ultimate limit state and serviceability limit state. And here is correctly assigned the accidental fire, Vibration we will do later on. I let the software now calculate, because this gives me the opportunity to show you the printout report a little bit more detailed. But maybe you already asked yourself, okay, it's nice that I can connect several models within one model and have the forces from all of them, but how can I do the documentation of this? I mean, I cannot say to the other engineers, I have magically just have the forces somewhere here. You probably need the documentation for this. And that is what I want to show you during the calculation. And here I'm opening again the model with the story 4. And here you have an option. Oh, wait, we have to get a little bit better. And this, so for example, what you definitely want to have in your documentation is the reaction force from the story and probably a whole bunch of other parts, but I don't have the aim to make you a complete printout report. I just want to show you how to connect several parts of the other model into this one model. Okay, so let's say we have this story 4, and once again, this is connected to story 5, 6, 7, 8, to all the other stories in here. And this is something I want to print to the clipboard. And then when I go into the printout report from the model where I'm working on, I can say, okay, this is from story 4, say okay, and have it imported. And while it is loading, I can, for example, open another model. Let's say this one. It's maybe not so interesting to have, but let's say we want this with 25 meters and each story also into the global printout report. You can have that here. Of course, right now it's not over the whole front, so this is something, oops, you always can change via right click properties, maybe no comments, whatever. So this is all possible. And one other point that is possible is to say, okay, I don't want to have it from another model. I want to have PDFs and unify them into one big printout report. This is also possible in here. For example, I'm just copy the load from the story 13, so the top story in here. And when I go once again, insert PDF and select this one here, go opening, and for example, I say all pages. There is a whole bunch of options. Import it, and then I also have this PDF inside it. Okay, these are the options we have for the printout report. Maybe just, I don't want to take a too detailed look into the printout report, but of course, when you go into the settings of it, you have all options to for example, regard the fire resistance configuration. Oh, sorry, this is in German. Oh, this was my fault. Once again, so we probably should change the language into English. Okay, but this is also possible, similar to the software. It's also possible to change the language. Okay. Yeah, that's because, so here you see, now it's there. And we have the language in English. So that's also possible. Okay, so that we don't need. I think the calculation is now ready. Yes, so that's fine. Oh, now this, now it's loading all the points to the printout report. That was maybe not the smartest way of doing it. I should have left that. Okay, but we can maybe wait a few seconds. Now it's ready. Okay, because it's now loading all the stuff from into the printout report that I should have skipped. Okay, so the design of the structure is ready. And the overview at first says, yeah, not really a bigger problem. When we look for the design ratios on the member, that looks quite okay in here. We can also take a look on it graphically. Maybe we take a look at the biggest loading for ultimate limit state. This is the bending. Oh, we can also take a look at the compression, maybe just to have an example or an imagination. So you see, yeah, 50% loaded. The length is definitely too long that I choose in here. And maybe we can also decrease the size of the section. Anyway, okay, but here's the pressure support verification done, and you have an equation that you can put also to the printout report. Then have a nice documentation of it. Okay, serviceability limit state without the vibration is also not really a problem in here. And fire resistance, we also take the biggest loaded area or beam, not area. And because I think it's always interesting to see how this is done. So the original height was 32 centimeters with a width of 16 centimeters. And because of my burning rates and my fire exposure on the sides, it is reduced to 6.2 centimeters and a height of 27.1. And then the verification, in this case for bending, is done again with this reduced section. Okay, that's the beams. And now we will jump to the surfaces. And here you see already, ooh, the fire resistance, that is not really so nice looking in here. I mean, it's only a small part of the structure. Oh, hold on. We will get the graphics on again because I skipped that. There can also be defined an average region or a surface result adjustment, just like I did in this part here. That would definitely be possible. And I say 20–30% is something that is probably possible to have it, at least if it's such a tiny high peak in here. It's something you can always do, but I want to try something different in here. Before we do that, we take also a look to the other loadings inside here. Yeah, the shear is for the punching through area is design giving in here on this part. That's the usual punching through area, what you want to take a look on. And we can maybe also take a look at the stress over the whole section, because I think that's always nice to see. And you see for the bending, okay, how the stress is transferred into each layer of our section or our surface. Okay, serviceability, okay, that's just deflection. We can take a look also on the details, but I want to show you that via the vibration analysis later on. You see, it's just that we take the limit deformation of 60 millimeter and use this for dividing the existing deformation in this serviceability state. And that brings us to the fire resistance, where we have this high overloading. Okay, there it's quite interesting when we look for the result diagram that I showed you for the ultimate limit state before, because now you see our intelligence behind it. You see, because of the burning, the fifth and the fourth layer is burned completely. And this is not only for the stress, but also for the stiffness. The stiffness matrix that I showed is reduced for the load combination 9 and 10. And yeah, you see, of course, now I have only one layer in here taking stress, because these other ones has in this direction where I'm looking on the stiffness 0. So that's, yeah, of course, the worst case that could happen. So 90 minutes with this glue that I'm using here, it will never work, I think. So that's just quite too ambitious what I tried. We nevertheless, before we change something, we will use it again in here and take a look at the charring depths inside. So layer 5, I told that already, it is burned completely, of course. By 90 minutes, there's nothing to talk about. But the layer 4 can be quite interesting, because you see, I usually had a remaining thickness of the layer of 2 millimeters, but because of this rule that I just showed you, it is burned completely now and has no more bearing capacity. So it's defined to 0. Okay, yeah, you probably expected what I'm doing now, because I introduced that long time. The easiest way to increase this now is to use a heat-proof adhesion of cross-laminated layers, because now I don't have to double the burning rates. And you saw it probably that it tells me that it needs to delete the combination 9 and 10. Why is this necessary? Because the stiffness in the combination 9 and 10 is also reduced by this new charring rate. So we have to export the stiffness matrix for this combination back again into the program, get the inner forces, and calculate it again. And hopefully now we cross our fingers. We hope that it will work. Okay. It should usually not take that long, because we only have these 2 combinations, and also for the timber design or the timber verification, it's just in brackets just the fire resistance where we need to do the stress analysis again. Still, I know there are a lot of parts to be verified. Yeah, and there we are already. I'm just scrolling a little bit through the questions, but Gerhard, yeah, he answered them all. And there's not really much questions coming doubled. What can we take a separate look on? No, I can't really see it. Okay, so yeah, but there we have it. I would have shown something else, but now we have the results. And then we directly jump into the surfaces and look to the fire resistance. And yeah, perfect. You see, I like nearly have 100% less loading on the structure, because yeah, just by this better glue that I'm using in here. And now we can also take a look to this graphics again, and now you see it already in the graphic. 14.5 millimeters do remain. And yeah, when we take a look at the stress, yeah, of course, this bottom layer here just gives me so much more load bearing capacity, that it's, yeah, just the smartest, for me, the smartest way to do it. In the details, you will definitely see the same in here when you go to charring depths, and then you see here that this is still working. So yeah, once again, this is really a big jump. I don't know a software out there that is calculating 2D surface elements, assigning a fire resistance verification by also reducing the stiffness. I mean, there's probably some softwares that will reduce or have the reduced section, but they will not reduce the stiffness. So, and it's quite so important if you look for the effects that it has in here. So that is what we are, yeah, very proud of, that we have it in our software now. And I think, yeah, it's one of the best things you can have. Okay, this, and now was only missing the vibration analysis. Yeah, I want to show you the simplified vibration analysis at a first step. Therefore, I'm shutting off the combination wizard and will just define one more additional design situation for vibration, of course, vibration, and have in load combination also one more load case that I'm assigning to this, and have 100% of the self weight and 30% of the live load, right? And yeah, I don't think you want to see the calculation again for all the other objects to design, and therefore I'm just doing the simplified vibration analysis again. You see, now I have only one combination and only deflection that I'm showing in here, so that would be quite good and quick. That's the point what I want to have in here. You know, the simplified vibration analysis is similar to the SLS verification with it's looking where is the biggest deformation, and this is divided then by the limit deformation of 5 millimeter. I showed it to you in the configuration settings, and you see everything's red. That's not nice. If you look for the members, there's not really a problem in here. But of course, for the surfaces here in this area and in this area, you have the biggest overloading. You have 44.8% overloading of it. Now, how can you regard that? There are several ways how to do this. What we here in Germany do the most of the time is to do the analysis by so-called Hamm-Richter. What does that mean? It means that we are calculating the frequencies of the structure. Therefore, I'm copying or assigning a new load case and give it the analysis type modal analysis, and import the load case 1 as a mass in here. And I need another load case for the stiffness criteria. This is the way how this is done. I will just show you what it means. So when we look for the static analysis in the load case 3, we will calculate the frequency or the heart rates of the structure. And now in this method is a rule that when you are in independent structures, you should be above a heart rate of 8. And when you are in dependent areas, so when your own family is introducing the frequency, you should be over 6 heart. Okay, so that worked for the second rule, but not for the first one. Okay, so you have two ways to do it. You can either get it stiffer, but it's not really in this problematic part. It's more in this part here where you can try to arrange something. But if you argue, okay, I have maybe a dependent area here, it is fulfilled at here. At least it is not 44.8% overloaded. And now the second criteria is that is the stiffness criteria. Therefore, in the maximal deformed part, you have to define a force, a single force of 2 kilonewton, and it should be below the deformation level of 1 millimeter. And when this is fulfilled, your verification is done. Well, it requires that you have an option to calculate the frequency rate, and this method is even more, or it can be even more sophisticated at what I'm showing in here. And it would also be possible to analyze this with our software. but there you have then to define a vibration on the structure and see how the damping in the structure works. So, but as with these rules, we are below the level of 1 millimeter, you can agree or you can argue that the vibration is fulfilled and that it is okay. Just as an option, because yeah, the simplified approach is really simplified. That's in the nature of such things. Okay, then I see everything's answered. That's always good. And we will come back to the presentation because Gerhard wants to tell you a little bit about new things upcoming. I already announced a little bit an upcoming webinar for stiffening, and Gerhard also has something in plan what he will do in future. Okay, but Gerhard, the stage is yours.
Thank you, Bastian, and thank you for the webinar. Yeah, so at the end, I want to talk about new features which we have implemented in the last, let's say, weeks. So last week we have released the fire design for surfaces. So it's not only for CLT, but for all kind of surfaces, for Eurocode design and for design according to the code from Switzerland, the CR 265. Yeah, and yeah, I will prepare a webinar especially based on the fire design, but I don't have a date yet, so maybe end of March or April or something. Okay, so the next feature was sorry,
sorry,
you are too fast.
Quick, sorry.
Yeah, no,
because you said next, yeah.
No. The next feature was we have released a few weeks ago. Is the profile sections according to our material database, also for the code from Switzerland. And this week we have released the design of user-defined cross sections created by R section, our standalone add-on. So now you're also able to design these cross sections for Eurocode and SIA code. Yeah. Okay, Bastian, next slide.
Okay.
Okay, here we talk about future features. So these are the features what we're working on. So we will release maybe next Monday or the Monday after next Monday, we will release semi-rigid links. So at the moment we have the rigid links, but in a few days you will be able to assign also line hinges inside the rigid links, which is also good. Yeah, for example, for composite beams and so on. So you can connect them, or you can connect now different or multiple members, via the rigid links. Okay, then the NTC. So for our Italian customer, we are close to release the NTC code. Let's see, maybe a few weeks more than it's finished. That's a national code from Italy. We want to try to extend the design supports for tapered and notches, but this feature will take a few weeks more, I guess. So we haven't started, but it's quite asked frequently. And the next big step is we plan to release a new surface type to model timber frame walls. So you can see it here on the bottom right side. We will release it step by step. So in the beginning, you can only model, or you can only consider it for the stiffness. So there is no design done, but and only for simple surface shapes. But we will release another feature step by step. So, but this will take at least a few weeks or at least months, I guess. So this is the forecast for the next year, I would say, and let's see. But just to inform you, and hopefully it will help you. Okay, Bastian, then I want to say thank you and goodbye from my side.
All right. I would like to close the webinar and once again invite you to the Digital Bau in 2 weeks or in less than 2 weeks in Cologne. Book your live demo there, and maybe Gerhard, no, go ahead, not, but me and the other colleagues can show you something. In case you cannot attend to the exhibition, book your free online appointment, contact our sales team. We have free online services all on our homepage. The models to download, I showed you, FAQs, and the GeoZone tool is there, for example. We are in the social media. Trial license, in case you do not use the software, just download it there and have a 90-day free trial of it. Okay, thank you and have a nice day.